We're off to chapter 11. So we're getting into obviously organic chemistry. And as I mentioned before, this pretty much is no calculations, which some people really like better. You can leave your calculator at home. And it is basically memorization. It is sort of mechanisms, naming, and those type of stuff. So let us get into it. So really, organic chemistry really is all about the study of carbon compounds. So the basis of all organic molecules is really carbons attached to carbons. And attached to those carbons, in most cases, are hydrogens. And one thing that, as we've talked about before, and one of the major sort of characteristics of organic chemistry is the idea that a lot of them are nonpolar or have a lot of nonpolar parts to them. And that is because our bond between carbon and carbon is a nonpolar bond. And our bond between carbon and hydrogen is also nonpolar. So a lot of organic compounds will be nonpolar. Which means, for example, they're not going to be very soluble in something like water, which is a polar molecule. Remember, for things to really sort of mix together and work right, it has to be what is sometimes referred to as like dissolves like. So polar and polar things are soluble in each other. Nonpolar and polar things are not soluble in each other. And nonpolar and nonpolar things are soluble in each other. One of the basic things of organic chemistry is that carbon, and I can't emphasize it enough, carbon has 4 valence electrons, and carbon should always have 4 bonds. And I say that because, as I might have mentioned, people, when they start drawing organic compounds, like to just keep on throwing bonds onto carbon, and they end up with a lot of bonds at some point. But keep in mind that it should only be 4 bonds. It needs to follow really the same thing we talked about when we talked about Lewis structures, which is the octet rule. Everybody needs to be there. There are different types of organic compounds, and we get those really from kind of substituting out hydrogens for other elements like oxygen, sulfur, nitrogen, phosphorus. Those halogens in group 7 can be substituted out. And they'll give us some different types of organic compounds. And they'll also turn some organic compounds into being able, for example, to basically interact with something like water. So they may end up with a polar group, even though a lot of it is nonpolar. There will be sort of a section that able to, for example, interact with water. So by changing out some of these hydrogens to some of these other elements, we do end up with some different properties that we see for these organic compounds. Based on sort of what's attached. A couple of things about organic compounds. They obviously have covalent bonds. It's really all about non-metal. Non-metals basically interacting, which means they will be sharing electrons. In some cases, that sharing of electrons will be equal and be nonpolar. In other cases, the sharing of electrons will be unequal and become polar. Because they are nonpolar compounds, organic guys typically will use what's referred to as dispersion forces as their way of interacting with other molecules. And that's basically the way to interact with other molecules. And that really is the major sort of force that works with nonpolar molecules when they interact with nonpolar molecules. And the problem sometimes with dispersion forces is it is like the weakest of all intermolecular forces, which means that is why they typically do have low melting points and boiling points, especially when you have nothing but carbons and hydrogens involved. And that's because this force that holds one organic molecule together with another is pretty weak, which means it doesn't take a lot of energy to break them apart, which is basically what happens sort of as you go from the melting point. They're separating from each other a little bit, and definitely at the boiling point, when you go from liquid to gas, they're easily sort of separated from one another. That's also why, as you may be familiar with, some of the simplest sort of organic molecules They typically are found in the gas state, things like methane, propane, butane. Those are all gases under sort of normal conditions. And that is because they're held together by really sort of weak forces. They're sometimes referred to as being volatile, which is why sometimes when you do organic labs, they will leave a lot of that stuff inside the fume hood because it could go into the gas phase really easily, and nobody wants to inhale all that stuff because they can go very simply into the gas phase. Also, because they could go into the gas phase, a lot of those organic molecules are very flammable, right? We use methane, propane, butane. Basically, a little spark and some oxygen, you have fire. So methane is what comes out when we do our Bunsen burner, right? And like propane, if you're trying to cook barbecue sometimes, right? We use those type of things. Because they are typically non-polar, they typically will be insoluble in water. And that's typically what happens is they will really separate out, that being kind of like the oil or organic guy water layer here. Typically, the water layer is on the bottom, or the aqueous layer is sometimes referred to, and typically the organic guy, or the non-polar guy, is usually the top layer when you kind of put those two guys together. And when you have like an oil spill, all the oil basically floats around on the surface of the liquid. Now, organic and inorganic compounds, again, there's a major difference between them. Inorganic compounds are pretty much everything we've been talking about up to this point. Inorganic compounds are ionic, for example, which are our metals and our non-metals together. And those are very soluble in water because when they do break apart, those ions get surrounded by water, right? And with the hydrogen side being attracted there, and here the oxygen side being attracted. That's really how something dissolves. An ionic compound dissolves in water, is they really get surrounded by the water molecules, because water is polar. Which means it has a side that is more positive and it has a side that is more negative. So that works really well with ionic compounds. Here's again just a table from your book. It's some of the differences between organic and inorganic. But again, the major difference, typically organic nonpolar. Most inorganic things are ionic. And again, those lower melting points and boiling points we find in organic compounds versus our inorganic compounds. Which, as you can see here, has a much higher boiling point and melting point than our organic guys in this particular example. So if we want to identify the characteristics here of most typical compounds that are inorganic are organic. If it has a high melting point, those are typically our inorganic stuff, right? They're not soluble in water, will typically be our organic. Has a formula of CH3, CH2, CH3 will be organic, right? That's really the basis of most organic things. This will be inorganic here. Magnesium chloride, it burns easily in air, should be organic, and has covalent bonds, would be organic. Hydrocarbons are organic compounds that pretty much, as the name implies, have basically hydrogen and carbon together. And they're basically made up of all basically carbons and hydrogens. We have what are sometimes referred to as saturated hydrocarbons, and saturated hydrocarbons are carbons that basically have the maximum number of hydrogens that they can have. So in order for carbon to have 4 bonds in an organic compound, pretty much once you run out of all the other elements that you need to put on there, pretty much we use hydrogen to fill it up to get the 4 bonds. So that's what we do there. And hydrocarbons typically will have all carbon-carbon single bonds, which are also sometimes referred to as alkanes, which is a group of organic molecules that have basically just those carbon-carbon single bonds. And because they have carbon-carbon single bonds, they will basically end up with the maximum number of hydrogens that they need to get to 4 bonds for carbon, or each of the carbons that are present. As we'll talk about in a second, unsaturated hydrocarbons basically do not have the maximum number of hydrogens that's necessary. Because carbon can make 4 bonds, it has a certain geometry associated with it. So if we look at our carbon in the middle, that is 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. It also has 1, 2, 3, and 4 bonds. As you remember from the geometry and Lewis structure chapter, 4 electron pairs of 4 bonds has a shape of tetrahedral. So these carbon-carbon single bonds in our hydrocarbons will have a bond angle of 109.5 degrees, which is what we see in tetrahedral. And that is a lot of times why hydrocarbons or alkanes are sometimes drawn in this sort of zigzag shape when they are drawn. And that is because the tetrahedral shape. So they kind of twist and twist and twist, and they end up kind of zigzagging back and forth when you have that. By the way, what I just drew here, as we will talk about, is what is sometimes referred to as line structure. And everywhere pretty much the line ends or 2 lines come together, those are all carbons. So in this case, that would be 5 carbons that are present here. Each of the little dots represent a carbon. You don't usually put the dots, by the way, in line structure. And because carbon needs to have 4 bonds, we would technically have hydrogens at all those other places. So that guy at the end would have 3 hydrogens because it has 1 line coming in. The guy to the left here would have 2 hydrogens because it has 2 lines coming in. This guy would have 2 hydrogens because it has 2 lines coming in. This would have 2 hydrogens. And the guy at the end here would have 3. Again, the idea here is to get carbon to 4 bonds, each of those carbons. And the way we pretty much do it is by using hydrogens along the way. Any questions on that there? Yeah, so if we wrote it out, what I just drew there, it would be CH3, CH2, 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 and CH3. This is what is referred to as the condensed formula. So that is the condensed formula. This is what is sometimes, as we will see in a second here, the expanded structural formula. Here, and basically the only difference really between sort of the expanded structural formula and the condensed formula is we kind of draw out the hydrogens. Basically, each of the hydrogens gets drawn out, kind of like a Lewis structure. With line structure, although I did put all this stuff on here, we typically don't do any of that. We just draw it like that, basically. Nothing else present. Any questions on that? Yeah. So as we just kind of looked at here, here are some of the different types of structures that we will come across. Most of the time, we probably will be drawing either the expanded structural formula or the condensed formula. We usually don't draw the ball and stick model or the space filled model. We sometimes will use wedges to indicate whether or not the hydrogen is coming front and back, but in this class, probably not too much. So really those last two, the expanded one where you really draw out all the hydrogens, or the condensed one where you don't draw out the hydrogens, are really the third one that we would use most of the time would be like a line structure. So those are the 3 most common sort of structures that we'll use in organic chemistry. And again, they do represent each of those guys as well, the structure. So here's ethane. So here's ethane, which has 2 carbons. It has 6 hydrogens. And this is a saturated hydrocarbon because, frankly, each of those carbons have 4 bonds, and they have the maximum number of hydrogens that you could put on there without going over the octet rule, and basically 4 bonds. This is, again, the condensed structural here. It is important to remember that although in the condensed structure, it does appear that if we look at it, the connection there is between hydrogen and carbon. It is not. It is still the connection between carbon and carbon. And that is still, as we see in the expanded structure, that is really how they are connected. So sometimes people get confused and think that it is the hydrogen that's connected there to the carbon. It cannot be the hydrogen connected to carbon because hydrogen should have how many electrons? Hydrogen should only have 2 electrons total, right? Which means if you did this, that definitely has more than 2, yeah? So again, in the condensed formula, we have that sort of way we write it, typically CH3, CH2, CH2, however many you got going on. CH3, but remember that the connection is between the carbon and the carbon. All right, so in butane, we want to predict the shape around each carbon. So let's take a look at it. So once again, when we're doing our shapes, we want to look at electron pairs and also number of bonds. So once again, that is 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 4 bonds. So this guy would be, again, tetrahedral. This guy in the middle, we would actually do the same thing. We would go 1 electron pair. We would go 2 electron pairs. We would still count this one, which would be 3. This one would be 4. That is tetrahedral as well. The one next to it, we would do the same. It has 1, 2, 3. We still count the guy to the left. So that is 4 electron pairs and 4 bonds, which would be tetrahedral. And as you maybe could imagine here on the last one, it is going to be the same here. 1 electron pair, 2 electron pairs, 3 electron pairs, and 1 more makes 4 electron pairs and 4 bonds, which would be tetrahedral. So the geometry around each of these guys would be tetrahedral. And again, that is why in line structure, we typically will see something drawn like this, which is again more of a zigzag shape because of the geometry that is present. And again, that would be 1 carbon, 2 carbons, 3 carbons, and 4 carbons that are there. This right here would be this guy, and next door would be this guy. Next door there would be this guy, and at the end would be this guy. So those are where each of those parts basically correlate to in the structure. Any questions on that there? All right, so let's talk about alkanes, which is really the simplest organic molecules you could have. They're also really the most important because everything that we do in organic chemistry all comes back to these alkanes. Everything in terms of naming, everything is based on the alkanes. Alkanes have functional group, and a reminder that a functional group is really the part of the organic compound that makes it a specific type of organic molecule. Is kind of really the, if you will, sort of the active part, if you will, of the organic molecule. It is, as we will see when we look at reactions, it is pretty much where everything occurs. It is also, when you look at the functional group, also how you go about naming it based on what functional group is present. So functional groups are really important, and there are many different types of organic compounds based on those functional groups. They all have slightly different names based on which functional group is there. They also have slightly different properties based on which functional group is there. But regardless of all of them, they all come back to this guy right here. They all come back to the alkanes, and that is really the basis of everything that you do in organic chemistry. Alkane's functional group is really the carbon-carbon single bond. Sometimes people say it doesn't have a functional group, but it really is a carbon-carbon single bond. It has to be carbon-carbon single bonded, which means, in most cases, it will be saturated. They have a general formula of CnH2n plus 2. And the N here is basically how many carbons there are. So for example, if we had 1 carbon, N would be 1. 2 times 1 is 2, plus 2 is 4. It should have 4 hydrogens, which is methane. If we had 2 carbons is N, so 2 times 2 is 4, plus 2 more would be 6 hydrogens, and this name is ethane. We have 3 carbons, N would be 3. 3 times 2 is 6, plus 2 more is 8. This is what is known as propane. So these are a few of the first sort of alkanes. And you can see a couple of things. They end up with ANE at the end of the name, which matches the sort of group that they are. That is an alkane, so that's a good way to do it. These are all single bonded guys that have basically hydrogens attached. What we're looking at here is 6 carbons, so N would be 6. 6 times 2 is 12. plus 2 more is 14 hydrogens that it has in that particular case. And that's what we see here in this picture coming through here. 1, 2, 3, 4, 5, and 6 carbons. And if you count up all the hydrogens there, we have 14. Each of these carbons have the maximum number of hydrogens that they could have based on the bonding to carbons next to them. And that means that this guy, again, is a saturated hydrocarbon. You can see the zigzag shape of how it is drawn because of the tetrahedral geometry that there is. And what I just drew there is really the line structure for this guy, which obviously would look something like that, I think. 1, 2, 3, 4, 5, and 6 here. By the way, this is what is known as hexane, ANE. So alkanes always have single bonds. They always have that sort of connection of basically 2 times the number of carbons plus 2 for how many hydrogens it should have. Hydrocarbons that contain only carbon and carbon single bonds and carbon hydrogen bonds can be formed in a couple ways. They can be a continuous chain where we have just a straight run of carbons that go straight across. This is sometimes referred to as a straight chain. It's basically just one, however long run of carbons in a row. We could also have a lot of organic compounds where they're sometimes referred to as being branch, which again means that they have kind of like a main run of carbons. And then every so often, maybe they got another run of carbons that kind of come off the main part, kind of like a branch on a tree, for example. And that's why it's sometimes referred to as branch chain. All these guys would have the appropriate number of hydrogens to get carbon to 4. That's how I know how many hydrogens to put on there. I look at how many lines they have and put the right amount of hydrogens in there. So this is sometimes referred to as a branch chain. And again, the main sort of run, really the main run here is actually, so I'll just do this one, but you know, we kind of have this main part, and then there are these branches that come off, even though that's really not the longest carbon chain, but we'll go with it for that. We've got these branches to come off. We'll also see as well, they can come together and make like a ring structure as well. And to make a ring structure, basically here, you know, these two guys will sort of close up on each other. And for example, you know, we could end up with maybe a ring type structure that looks something like this. It's sort of a closed system here of an organic compound. A lot of times the ring type structures are drawn in line structure, like a square, a triangle, whatever it may be. Now, when we go to name these organic compounds, we do use what is referred to as the IUPAC name, and that's the International Union of Pure and Applied Chemistry. These are really the guys that come up with all the rules that we follow to name things in chemistry. So you could thank them, I suppose. But all alkanes will end with the ANE sort of ending. A lot of them will use a Greek prefix depending on the number of carbons that are present. By the way, when we do sort of close this guy up into a ring type structure, we do have to sacrifice a couple of hydrogens. Otherwise, carbon would have too many bonds. So for example, if I just directly try to connect these two, the problem would be that carbon would actually end up with now 1 bond, 2 bonds, 3 bonds, 4 bonds, and 5 bonds, which is too many. So always in organic chemistry, when we add a bond, you pretty much have to sacrifice 2 hydrogens, and 2 hydrogens come off of each of the carbons that are involved in the bond. So wherever you add the carbons together, you usually will sacrifice a hydrogen. So really in this case, we would get rid of a hydrogen there, and that will allow carbon not to have more bonds than it should in this particular case. So if we look at this particular one, this has 1 carbon, 2 carbons, 3 carbons, and 4 carbons. and it has 2, 4, 6, 8 hydrogens. So that is C4H8. When you go into a ring structure, this has a formula of CnH2 times N. Yes. And that's different than a straight chain alkane or even a branch chain alkane because they have to lose those 2 hydrogens when you make that extra bond in that particular case. Any questions on that? Now, we also talked about earlier kind of saturated hydrocarbons. And so there was a question of, why is it saturated? Since we're kind of talking about losing hydrogens here. When we look at something like this, which is again a saturated hydrocarbon because it has the maximum number of hydrogens that it should have. If I take the same 2 carbons but want to make a double bond there, the problem is I cannot just leave it the way it is and put the double bond there, because now again each of the carbons on each side has too many bonds. It has more than 4 bonds. So once again, in this situation, when we add 1 bond, we actually lose a hydrogen on each of the carbons, and that allows it to maintain the correct number of bonds, correct number of electrons. This is what is referred to as being unsaturated hydrocarbon. And this is unsaturated because it does not have the maximum number of hydrogens on the carbon like this one. Technically 2 carbons, if you want to max out the hydrogens, should have 6 hydrogens, but because we had to put that double bond in there, it becomes what is known as being unsaturated, and it does not have the maximum number of hydrogens. So that really is sort of the difference between something that is saturated and unsaturated. By the way, if I wanted to slap on here a triple bond between those 2, I would once again have to, bless you, lose 2 more hydrogens. So I would have to take off, for example, 2 more hydrogens there to make the bond. And this guy would have obviously the correct number of bonds and also be unsaturated as well. By the way, when we put these bonds on, as we will talk about, these are different types of organic molecules. These are alkanes, these are alkenes, and these are alkynes. Yeah, and they are all different types of organic molecules. They have a carbon-carbon single bond as its functional group, has a carbon-carbon double bond as its functional group, and has a carbon-carbon triple bond as its functional group for each of these things. So these are all different types of organic molecules, but they're all still based off of the alkane, which is really the most important thing. The most important thing whenever you look at an organic compound is really how many carbons there are. For example, as we talked about a second ago, this guy is basically C2H6, and this has a name of ethane, ANE, as it is an alkane. When we make it unsaturated, we do lose those 2 hydrogens, which means alkenes, ENE, have a general formula of CnH2n. So if we look at this guy, this is C2H4 is what we have here. This name is still based off of the alkane name, which is ethane, but because this is an alkene, this is what is known as ethene, ENE, at the end of it. This is an alkyne, which also still has 2 carbons. It, though, has a general form of CnH2n minus 2 because we had to sacrifice 2 more hydrogens when we made that triple bond. And if you look at the formula here, it has 2 carbons and 2 hydrogens. So the alkane is named ethane, ANE. The alkene is named ethene, ENE. If you had to take a guess here, this guy is named ethyne to match the alkyne sort of name. So that would be the name. So as we go through the alkanes, it's really important to learn the first 10 alkanes, which we'll see here in just a second, both the name and the formula, because pretty much 100% of everything we deal with in organic chemistry always comes back to those names and also really how many carbons there are. Those are really the 2 main things that you look at, especially when you're trying to name things, is those 2 things. How many carbons there are, what is it based off of, and what is the functional group that is there, and you do some changes to those things. We clearly will go over all this stuff in greater detail as we go through this chapter. Yes. Any questions on that so far? Why is it what? Why is this one or? That is the general formula for how you figure out how many hydrogens there would be in an alkyne. Because it has a triple bond, you have to lose 2 more hydrogens. So in this case, it has 2 carbons, which means N would be 2. 2 times 2 is 4. I'm sorry. And 4 minus 2 is 2. Yeah, so that's how you get down to 2 hydrogens, which is the 2 hydrogens it has. Yeah. So basically 4 minus 2 would give you the 2 hydrogens. That's just a general way you could figure out how many hydrogens that alkyne could have. Just like this is the general way you could figure out how many hydrogens an alkene should have. And this is the general way, wherever we were looking at it before, CnH2n plus 2 is the general way you can look at how many hydrogens an alkane could have. Other questions? All right, so let's get into some of this here, maybe. So we started looking at some of these. Let's talk really about the first 10 alkanes, which is really important. 10 alkanes. All right, so we did a few of them. Again, each of these have CnH2n plus 2. So again, our 1 carbon would have 4 hydrogens when we put it into this formula. And that again has a name of methane. Our 2 carbons, 2 times 2 is 4 plus 2 is 6, would have 6 hydrogens, is ethane. Our 3 carbons, 3 times 2 is 6 plus 2 more is 8, would be propane. Our 4 carbons, 4 times 2 is 8 plus 2 is 10, would be butane. 5 carbons, 5 times 2 is 10 plus 2 more is 12, which would be pentane. 6 carbons, 6 times 2 is 12 plus 2 more is 14 hydrogens it should have, is hexane. 7 carbons would have 7 times 2 is 14 plus 2 more is 16, which would be heptane. 8 carbons, 8 times 2 is 16 plus 2 more is 18, would be octane. 9 carbons would have 20 hydrogens, would be nonane. And lastly, the first 10 here is 10 carbons would have 22 hydrogens, and that is known as decane. The faster you learn all 10 of these names and the formulas of how many carbons go with it, the much better your organic life will be. Yes, so I can't emphasize that enough. Make sure that you learn these. Again, everything is pretty much based off of those 10 guys' names. All right, so why not? I'm just gonna freehand it here. Why not? Let's talk about how we go about naming alkanes properly. First off, when we go to name alkanes, really the first thing that you want to do is always find the longest carbon chain. Now, when we look for the longest carbon chain, it does not have to be the straightest. It could go straight, it could go up, it could go over. Again, the only thing that you cannot do when you're counting the longest carbon chain is go backwards. So once you go in one direction, you pretty much have to keep counting until you hit a dead end. You can't go back or anything like that. And when you find the longest continuous carbon chain, you should always check all your options. It may not always be the straightest. It may actually go up and over. Maybe your longest, it may even go this way, down and over that way. You do want to kind of check them all. But once you do, it hopefully should match one of those 10 alkane names we just looked at. And when you find that longest continuous carbon chain, that's going to be really kind of like the base of your name, is that longest carbon chain. Once you find the longest carbon chain, whichever way that it runs, there will always be groups that are not part of that longest carbon chain. And those are what are referred to as groups. So then you want to identify your groups that are attached. And they are sometimes referred to as alkyl groups, which are a fancy way of saying carbon containing groups. So let's talk a little bit about groups and sort of what we mean by that. And we'll just come back here to use these as sort of a reference point. So let's say we had something that looks like this here without an extra hydrogen in the middle. Let's say we don't have that guy. That's a do it. All right. So let's say we had something that looks like this, right? Okay. So the first thing that we would want to identify is the longest continuous carbon chain. How many is the longest continuous carbon chain in this case? It is 3, and we actually have a couple of different ways that you could get to 3. You could just go straight across, which would be 3. You could also go, once again, straight across and up, right, would give us 3. You could also, if you want to go this way and up, would give you 3 as well. So there are sometimes multiple ways that you could go, and sometimes they will give you the same number of carbons, and sometimes they won't. So you do want to kind of check all your options as to which way you go. You do not want to fall into the idea of, I'm just going to always just take the straight one across there, and that's going to be the longest, because it will not always be the longest carbon chain. So when we do this in this sort of simple example here, we'll just take when you do have more than one option, sometimes it's good just to take the straightest ones because it's maybe easier to see. That is going to be what we were talking about in the first step, which is find the longest continuous carbon chain. And in this case, that is how many carbons? That is 3 carbons. That means that the base of our name is going to be based off of propane, which is the 3 carbons. So that's going to be propane. That is what is sometimes referred to as the main chain, or the main part of the chain, the longest carbon chain. When we look at this, though, we clearly can also see that there is something else there that is really not part of that main chain, and that is that guy right there. And that is what is referred to as a group, or an alkyl group. It's a carbon-containing group. It is not part of the longest carbon chain that's present. That is what, again, is known as a group here. An alkyl group means basically, again, that it's carbon-based. It comes from an alkane, basically, is what it is. So just like the longest continuous carbon chain is based off of the alkanes, most of the carbon-containing groups that are not part of that longest carbon chain is also based off of how you name it, based off of the first 10 alkanes. So when we look at that group that's attached, how many carbons are in that group? That group that I put in a pink box there has 1 carbon, right? And 1 carbon is based off of methane. But because it is not methane, methane has 4 hydrogens, right? This group has only 3 hydrogens, yeah? The reason it has only 3 hydrogens is it needs that extra spot there to attach itself to that chain, yeah? Because if it kept the hydrogen and then tried to attach itself to the chain, how many bonds would that carbon end up with? 5, right? Which is too many, right? So it would end up with too many bonds in that case if it kept that hydrogen like methane. So it is based off of methane, but it is a group, which means, frankly, it has 1 less hydrogen attached to it. And the reason it has 1 less hydrogen is it allows it an ability to attach to the long carbon chain and not end up with too many bonds. So because it's an alkyl group, we drop the last part of that name, And this is what is known as a methyl group. Yeah. Any questions? Yeah, this guy in the pink box here would be what's referred to as a methyl group, because we're not going to count it as being part of the longest continuous chain. So that's sort of what you want to think about. You want to find that longest continuous carbon chain. You want to identify everything else that's basically attached to it, but not counted as part of the longest carbon chain. And those are what are referred to as groups. They will always have one less hydrogen than the alkane. And the reason, again, they have one less hydrogen is that gives them a place to attach and still have the correct number of bonds. And that's why they're referred to as a group and basically a YL at the end of it. So let's say I had, all right, now I'm going to add the hydrogens as requested. All right, so we're going to get carbon to 4 bonds. I'm going to put 3 hydrogens there because that carbon has 1 line going into it. The carbon next to it has 2 lines going into it, which means to get it to 4 bonds, I need 2 hydrogens. The carbon right below that has 3 lines, which means to get that carbon to 4 bonds, I need 1 hydrogen. Carbon to the left has 1 line coming in, which means I need 3 hydrogens to get it to 4. The carbon to the right here needs 1 hydrogen. Carbon to the right of that needs 2. Carbon to the right of that needs 3. Carbon down here needs 2. And this carbon needs 3. All right, the first thing you're going to do is find the longest carbon chain. And then you need to identify what things are groups. So take a moment, put a line or a box around the longest carbon chain, and then put some boxes around the things that are groups. And hopefully I didn't screw up. Let me see. The longest carbon chain, how many? It is 6, yes. So there's a couple of different ways you could actually get 6. If you went straight across here, that would be 1, 2, 3, 4, 5, which is not 6. That's 5. So we'll get rid of that. If you went straight across and then went up, that's 1, 2, 3, 4, which is obviously less than 5. So that's not good either. If you went starting up here, 1, 2, 3, 4, 5, and 6, that would get you 6, which is more than what we've had before. The other way you could get to 6 is, the other way you could get to 6, I believe, is you could go 1, 2, 3, 4, and then go down 5 and 6. Yeah, it doesn't really matter which one you choose, but it does look like 6 is our most. And again, when you do have options of the same longest, you can technically choose whichever one. The name should come out the same. So as long, the important part is as long as you find the longest carbon chain. As you can see in this example, may not be the straightest. You do want to kind of check all your options. The only thing, again, that you cannot do is backtrack. So you got to go one way until you dead end and then come back. So we know that the base of this name is based off of 6 carbons, which brings us to here. So the base of this name should be hexane, right? Is the base of this name. We now have actually 2 different groups attached to this one, right? That is not part of our 6. We have over here, which is a group. And we also have over here, which is a group as well, right? Now, we already talked about the guy on the left there. That is a 1 carbon group that's based off of methane. So that is a methyl group, right? This is a 2 carbon group, which means the name should be, it is an ethyl group because 2 carbons is based off of ethane, which means this would be a ethyl group. Yeah. Any questions on that there? All right, so those are really kind of the first 2 really important steps of naming something is longest carbon chain. Once you identify that, what groups you have. So let's talk about the rest of what we need to do with this. So we'll come back here to our name here. The next thing that you want to do is once you have the longest carbon chain, once you basically identify what groups are present, you want to number the longest carbon chain. And there really is sort of two ways to number it. And what we're numbering, by the way, are the carbons that are part of the longest carbon chain. So we're going to number them just like 1, 2, 3, 4, however many there are. You obviously could go left to right, or you could go right to left in most cases is kind of your options. And the purpose of numbering these chain is to figure out where the groups are attached in the alkanes. So the naming part of alkanes is all about telling somebody the location of where everything is sitting on the main part of the chain. The way that we actually do want to number is whichever way gives the groups in this case, and those are the alkyl groups, the smallest number. Now, in certain situations, it may not really matter which way, but in some cases it will matter. So we want to go whichever way gives the groups the smallest number. So let's go back, look at our two examples here. And in this case here, we'll go with numbering this chain. And again, it may be the same no matter which way you go, or it may be different. So if I numbered the longest chain here, this would be carbon 1, that would be carbon 2, and that would be carbon 3. The other option to number this guy here would be carbon 1, carbon 2, and carbon 3. In this particular case, it doesn't really matter which way we went, right? That group that's sitting there is always going to be at carbon number 2, regardless of which way that we went in this case. So we actually do add that to the name of the group. So this is really what would be known in this case as a 2-methyl group when we go to actually name it. And when we do name things, we always put a dash between a number and a letter. So if you're writing something that's a number to a letter, or even a letter to a number, you do put a dash between them. So that's why there's a dash between the number and the letter, is basically what we always kind of put in there. And again, letter to number as well. Now, if we were to name our number the bottom one, which I just made it up, so it might not make a difference which way we go, but we'll see here if it does. We could start numbering up on top, which means that would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, that would be carbon 5, and the guy over here would be carbon 6 going that way. The other way that we can number it is heading in the other direction, where this would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, that would be carbon 5, and that would be carbon 6. I guess I should have wrote it on the bottom there. I'll go that way. Not 25. There we go. All right. So let's see. Does it make a difference which way we go in this case? It actually does, it looks like. So I guess I did okay making one up here. So let's start with, it's actually red, the first numbering I did. When we do the red numbering, and the red numbering here, we have a group at carbon number 3, and we have a group at carbon number 4, right? Going in that red direction. Is orange, I think, is the other way. So going in the orange direction, we end up with a group at carbon number 1, 2, 3. Oh, no, I did not do so well here. It was the same. And also number 4, right? So we did end up here with the same way, no matter which way we go. So again, in this case, it would not matter which way you numbered it, but you do want to number whichever way is the smallest. So for example, in this case, this would be a 3-methyl. This guy would be a 4-ethyl, right? Perhaps. So we're going to decide if that is correct or not correct in just a second. Any questions on the numbering part? So in this particular case, we actually would want to do it the opposite way. And the reason we would want to do it the opposite way is rule number 4 is when we go to name these guys, so now that we got the longest carbon chain, we know the name of it, we got all the groups and we know their names and we know where they are sitting. We want to put the name like this. All of the groups go in alphabetical order. Regardless of number or prefix that may be there. So in this particular case, when we look at this bottom one, we have a methyl group, right, which is M, and we have an ethyl group, which is E. Which one should actually come first in the name? The ethyl. So since the ethyl group should actually come first in the name, we probably want to give it the lower number. So we actually would flip it around and actually do the numbering where this ethyl group would actually end up at 3 and our methyl group would end up at 4, just because really the next rule is there's no difference which way you go in numbering, but we will put these guys in the name in alphabetical order. So since we can in this case, might as well give them the smaller number alphabetical order in this case. Any questions on that there? In the case that you cannot, you go strictly by smallest number, regardless of alphabetical. But in a case where it's kind of like a tie, no matter which way you go, you can sort of do both things in this case. So that's what you would want to do, is try to do both things. What's that? Yeah, so in this case, it didn't matter in terms of the locations of where the groups are. They're both basically at 3 and 4, no matter which way you go. What the next sort of rule in terms of naming is, since you want to put those groups in alphabetical order, when you actually do name it, you might as well also give alphabetical order the smallest number. And it may not always be, you may not always be able to do that. You may have a situation where you go one way and it's like 2 and 4 is a group, and the other way is like 3 and 5. And in that case, you go with the 2 and the 4 regardless. You always want to go with the smallest numbering. So you always want to go with the smallest numbering, but sometimes when there is a tie, you then want to go to the next important thing, which would be alphabetical. Other questions? Yeah. All right, so when we have all these things done, we would actually give our name here for everything and put it in alphabetical order. So let's see how that one would go with our one that we were looking at the bottom here. I will start with this one here, son of a mess, but we'll kind of look at this one. So let's take a look at first that one, just to wrap it up here. So we had this one first, I think. All right, so our longest carbon chain was our 3 carbons, which means the base of the name here is propane. We had our methyl group up here. And again, in this case, it did not matter which way we numbered. That methyl group ended up at carbon number 2. So this would be 2-methyl propane. Again, a dash between the number and the letter. And you run basically the back names together, methyl and propane. Basically what that means is if you go backwards, propane means you have 3 carbons in a row, and a carbon number 2 of those 3, you will find a methyl group hanging out there. That's basically what the name basically implies. Now, if we were to put together the other one that we were looking at to really finish up here, what I'm going to do actually, I don't want to mess up redrawing it. I'm just going to kind of clear out all this stuff here. All right, so let's get all this stuff out of the way. All right, so putting this guy together with everything that we were talking about here, we're going to go with the base of the name, which was 6 carbons, which is hexane. We're going to go alphabetical here, which gave our ethyl first. So this is going to be 3-ethyl. We're now going to go from a letter to a number for the other group, which was 4-methyl, right? So that's going to be -4-methyl. And try to squeeze it in. Hexane, basically. Yeah. So going backwards in the name, hexane means we have 6 carbons in a row. And at carbon number 3 of those 6 carbons, we have a ethyl group. And at carbon number 4, we have a methyl group. Is basically what the name's all about. It's really just about giving everybody location of where everybody is at. Couple other things to finish up on. We did the number dash letter. If you happen to end up with two numbers, we do a comma between two numbers if you have two numbers in a row. And obviously we'll do some examples of those as we continue through. The other main thing here is alphabetical, two numbers in a row. If you have more than one group in a molecule, basically the same group, like say two methyl groups in an actual molecule, we do use prefixes, kind of like our non-metal, like di is 2, tri is 3, tetra is 4. So that would be something like if you drew something, I'll just draw the group part of it, like you had, say, two methyl groups in a compound like that, you would still give the numbers of where they're located. So we'll just imagine and pretend there's rest of this molecule here. Say that's carbon 3 and that's carbon 4. When we would go name something like this, this would be 3, 4 dash dimethyl, and whatever the rest of it would have been, obviously, with it. So we do use a prefix to indicate that there's more than one of the same group in the compound. And we still need to give the location of those groups, even if they happen to be on the same carbon. So if those two groups are on the same carbon, say carbon 3, you would have to go 3, 3 dimethyl and give the location of each of those groups. So we sometimes will use prefixes. And when we do alphabetical, it is without the prefix. So we would look still at the methyl as being the alphabetical part that we want to take care of. Any questions on that there? All right.